Okay, whoop whoop! Welcome to Logs of Log. We're not in the kitchen, so this isn't in the kitchen with Log right now. But let's chat about energy. I feel like I have had none, or you could say I've had a lot of potential energy, stored energy, not energy of motion lately. In chem, we talked about how potential energy is chemical potential energy and it's stored between bonds. And again, this idea of energy being conserved, we are still assuming to be true. So let's throw some energy into the reactions we've been talking about. You can't really sit there and look at a reaction and figure out how much energy a reaction has. But what we can do is we can measure the change in energy, aka the change in heat being from the reactants to the products. And that term for the change in energy, switch my colors here, we call that enthalpy. And because E is already used for just straight up energy, we use the symbol H to represent that change between the beginning and the end of the reaction. And we use the symbol delta just to represent that. We'll talk more about the units that we use to represent energy a little bit later, but you'll see the energy represented in calories, you'll see them represented in what are called joules, or my rap name, if I were to become a famous rapper, would be kilojoules, like metric, which is what kJ is, so it's the energy, and it's the energy per mole. And later on, get excited, we'll talk about how to calculate it, but I just want us to be aware of that this term enthalpy is the change in energy as we go from the reactants to the products, the difference between them. And we use two terms, which you may have heard before, to describe whether a reaction is gaining or losing energy. And the first term I want to go over with is what we call an exothermic reaction. And this is a reaction in which energy is exiting the system. I think of like an exoskeleton, something on the outside, giving off energy is the way to think about this. I'm going to draw what we call a potential energy diagram. Here is my energy over here, and here's like a time, maybe not necessarily a time vector, but just kind of our x-axis over here. In an exothermic reaction, I'm going to write here are the reactants. They are higher in energy than the products are that are being formed. So in order for this reaction to make the products, the reactants have to lose energy. It has to go down to go from the reactants to the products. So we would say that the change in energy is negative. Now picture, if you were holding a reaction and it is giving off energy, what would that feel like for you? Would it be getting cold if the reaction was giving heat off to you, or would it feel really hot? Exothermic reactions tend to feel warm, or you'll hear me use the term make the surroundings warmer. That's really bad handwriting, but warmer. I want you to picture like burning something, a combustion reaction. You're sitting by the campfire, hopefully some of you guys are doing that, and it feels warm. What type of reaction is that? You're a part of the surroundings, so that reaction, that combustion reaction, is giving energy off to you. Sometimes you'll see us write energy as a product because it is being produced, it is being given off in this reaction. So if I wrote like, here are the reactants, and I'm turning them into the products, you'll see people write like energy over here. You'll see like a kilojoules or a calories number. In an exothermic reaction, I want you to notice that the products are lower in energy than the reactants are. And so since they're lower in energy, we'd also say they're more stable. So if we were in class and I was getting you ready to take an exam for this unit, this little graph here would probably be one of the most important things to have on a note card, because you could kind of answer a whole lot of questions based off of this. If I asked you to draw this for an endothermic reaction, this is a reaction in which energy has to enter the system. It would literally just be flipped. So here's our energy. Our reactants would be down here, And then to make the products, you'd have to add energy to it. So the products in an endothermic reaction are higher in energy. So the change in energy or the change in enthalpy for this reaction would be positive. I wonder if I move my face. Oh, hey. If you were holding this, the reaction would have to get energy from something, and so it would literally take the heat from you. So picture that the surroundings, you being a part of the surroundings, would feel cold because your heat, your energy is being taken from this. This is why we sweat, because sweat evaporates. And in order to evaporate, those molecules have to absorb energy from you. And so it makes you feel cooler because those water molecules are taking away your heat. You will see people write energy as a reactant in this case. So right, there's our energy plus the reactants that makes the products. And so again, we can answer some questions. So in an endothermic reaction, which side's more stable? The reactants are. Which side's higher in energy? The products are. Fun? Fun. Great. Great. We talked about combustion. Let's do nail polish remover. No, let's not do that one. Let's do ammonium chloride and water. Something fun. Pause the video and try and write the dissolving equation for ammonium chloride. Okay, hit pause, try it. Okay, back. You hit start again? Okay. Ammonium chloride. I would have had us do this in class. First off, the formula for it is this guy. It's ionic, because ammonium's an ionic compound, is a solid. And when we put it in water, and write H2O above the arrow here, all ionic compounds, what do? Dissociate, which means they separate into the two ions that make them up. So we've got this guy, and we've got our ammonium ion and our chloride ion, and I'm going to write aqueous. Now in class, I would have had us do this with a thermometer, and they're not even letting me get back in the school to get a thermometer to like show you this. But we would have taken the solid, poured it into the water, stirred it with a thermometer, and we would have saw the temperature start to get cold. Do you see how water here is not really a part of the reaction? Water is technically a part of the surroundings. So if water was a part of the surroundings and it got colder, what type of reaction is it? Endo or exo? It's an endothermic reaction because the surroundings got colder. This reaction needed energy in order to make our products that are here. So I could write energy here. Or another way to write it, which get a little bit later, we'll talk about how to calculate the energy. You could write the same reaction, NH4 plus, I'm going to write aqueous, and Cl minus aqueous. Or the other style for how to write this is you could write at the very end, damn it, that clock. You could write that delta H is positive. So those are the two styles where you'll see us write energy kind of in a reaction. Like I said, here's one style. Here it's positive. Otherwise, we could write, whoops, I'm going to erase. We wouldn't necessarily write that it's positive here. You would write 27 kilojoules plus ammonium nitrate makes this. Okay. So again, two styles. We call this, just to be fancy, a thermochemical equation because it has energy in the balanced chemical equation. So don't stress too much about that. But what I want us just to kind of start to pay attention to is the energy and where that goes and what that necessarily like means for us. So on Class Kick, I'm going to put this slide on there. This is kind of your homework for today. I want you to try it. And what I want you to do is I want you to tell me if each reaction is endothermic or exothermic. So you would write either endo or exo. And I want you to tell me what would happen to the temperature of the surroundings. Would they go up or would they go down? So you would first need to figure that one out. Then I want you to tell me if the reactants or the products are more stable. So that's which one's lower in energy. Which side is higher in energy is the last one. Throughout the course of the day, I'll kind of go on class kick and check. But tomorrow, we'll start to kick it up a notch. We'll throw a little bit of stoichiometry in here for you. So, and we've got names for delta H's. We'll talk about that tomorrow. But that's it for today. Check class kick out.